If you are building large AI models, you definitely know the central tension here. Pre-training scaling feels almost like physics, right? Smooth, predictable power laws. You add compute, you get proportional gains.
Yeah, it's pretty reliable.
But then there's reinforcement learning, RL scaling. Well, it's historically felt more like alchemy.
It's totally a gamble.
Exactly. You try to scale up a run, stability just vanishes. You burn through massive amounts of compute, and you're left just guessing which tiny hyperparameter tweak might actually save the job.
It's been the ultimate bottleneck, honestly. For years, there just wasn't a reliable, predictive way to handle RL scaling. Teams were kind of locked into these brittle, ad hoc recipes.
Right.
But Meta just delivered something pretty monumental here. They did this massive, really methodical investigation into RL scaling, and they packaged their findings into a highly predictable framework they're calling ScaleRL.
Okay, ScaleRL. And that's what we're digging into today, the results of this huge study. Because this framework, it seems to give development teams something they've never really had. The ability to actually forecast where an RL run will land.
Precisely.
It feels like we're watching the sort of chaotic art of scaling RL finally turn into a proper engineering science, backed by real numbers.
That's the goal. And the really profound core insight they found is that RL scaling, fundamentally, it just doesn't follow those nice power laws we see elsewhere.
Ah, okay. So what does it follow?
Instead, performance follows a sigmoidal compute-to-performance curve. You can kind of picture it like a stretched-out S-shape.
An S-curve, right?
Yeah. And this curve has a clear ceiling, an asymptote, technically, and also a distinct slope that dictates how fast you actually approach that ceiling.
And the real gold for you, the listener, is this.
Yeah.
If you fit this S-curve early, like really early in your training process, you can stop flying blind. You can reliably forecast that ultimate ceiling before you commit to, say, a six-figure compute bill. And they actually validated this, right, over a huge run.
They did. The authors validated the whole methodology over a massive 100,000 GPU-hour run. It holds up.
Wow. Okay, let's start with the chaos then. Why has RL always been such a gamble compared to the predictability of pre-training? What's going on under the hood?
Well, the sources are pretty clear on this. RL runs are just incredibly brittle. The feedback loops are so tight, and they depend on these constantly changing data distributions.
Unlike pre-training, where you're mostly just throwing more data at it.
Exactly. RL introduces these tricky components, things like the off-policy setup, the specific loss function you use. And when you try to scale those, even small numerical stability issues can just get magnified massively.
Can you give an example of that magnification? What blows up?
Sure. Think about importance weights. These are basically multipliers used to decide how much an old piece of data from a previous version of the policy still counts when you're training the current one. Now, if your setup is brittle, those weights can just, blow up. They become numerically huge, totally erratic, and that leads to these sudden destructive gradient updates.
And that's why you see these runs just unpredictably crash when you try to double the compute or something.
That's often a key reason, yeah.
So how does shifting from this idea of a power law, which kind of implies performance goes up forever, to this new sigmoidal S-curve model actually help solve that instability and let us forecast?
Because the sigmoid saturates. That's the key difference. The authors model RL performance, and importantly, they measure it robustly on an independent validation set as this saturating sigmoid function of compute, which they just call $.
Okay.
And this gives us three parameters that really matter for prediction. First, there's the ceiling parameter, $8. That's your maximum possible performance, the asymptote.
Right, the top of the S.
Exactly. Second, the slope, $, or dollars. That's your predictive scaling efficiency, basically, how fast you climb that S-curve.
Your speed, essentially.
Yeah, right. And third, the midpoint, CT text-meter. That's the point where you're climbing the fastest, the steepest part of the curve.
Okay, so instead of just hoping performance keeps going up indefinitely, you can potentially calculate exactly where your performance is going to top out, even before you're, say, halfway there.
That's the idea.
But hang on, if I run a quick test for just, 2 days, why should I trust that short little curve fit to predict what's going to happen after 100,000 GPU hours? Isn't that just moving the gamble from the whole run to just trusting the early fit?
That's a really crucial question, the validity question. And the study addresses it directly. They showed that their early fit extrapolations tracked full, much longer runs really closely across multiple different setups.
So the predictive power held up.
It proved robust, yeah. They took their specific ScaleRL recipe, ran it for that huge 100,000 GPU hours, which is a massive budget, let's be clear.
Oh, yeah.
And the curve they fitted from just the early part of that run matched the final performance almost perfectly. So this is predictive scaling actually validated in the real world.
I can only imagine hearing the validation must be a huge relief for anyone who's ever had to, you know, sign off on one of those massive compute bills based on just seeing an upward trend on a graph for a few days.
Absolutely. And while, yes, these results were largely found by Meta using their large language models, the underlying principle that RL optimization performance saturates that seems pretty universal.
So it sets a baseline.
Exactly. It sets a robust baseline. Now, if a smaller team applies these ScaleRL techniques to, say, a novel robotics task or a completely different architecture, they have a standard curve to test against, instead of just inventing their own scaling expectations from scratch.
Okay, this is where it gets really interesting because this predictable curve exposes one of the field's biggest traps. The study calls it the bitter lesson of RL. What's the counterintuitive thing we need to stop trusting?
This is probably the costliest mistake RL teams have made historically, based on what they found. The sigmoid curve reveals that methods that look fastest, initially the ones giving you that quick pop in performance early on, often hit a lower, kind of immovable ceiling. Parameter dollars is just lower for them.
So they start fast, but plateaus sooner and lower.
Precisely. And conversely, methods that look slow at the start, maybe frustratingly slow, often have a much higher potential ceiling. They ultimately leapfrog those initially faster approaches.
Okay, give us the clearest examples of that trap in action. Where do we see this?
Batch size is a great one. Running with small batches gives you really aggressive, fast initial learning. Looks great on the early graphs, right? Great slope, parameter by dollar.
Yeah, makes sense. More updates.
But the study shows these runs stall out downstream. They hit a lower ceiling, a lower dollar. Larger batches, on the other hand, look slower to start, perhaps just because they take more wall clock time per update.
Right.
But they fundamentally lift that final ceiling. They allow for higher ultimate performance if you have the compute budget to reach it.
Wow, that is completely counterintuitive, especially if you're under pressure to show quick, positive results in the first week or two of training.
It absolutely is. And it's the same principle they observed with context length in language models. Short context moves quickly at the start, gives you fast early rewards, easy wins. But if your goal is truly maximum reasoning capability, you need that long context. It lifts the ceiling, parameter dollars. So this sigmoid fit becomes vital because it explicitly lets you separate that short-term efficiency, the slope dollars, from the long-term destination, the asymptote dollar.
So you use B to optimize your speed, but you look at A to set your expectations for final quality.
Exactly. You manage them differently based on your goals.
Okay, let's shift from the theory of the curve to the practical side. The study didn't just give us a theoretical tool, it actually distilled a stable, reproducible kind of house style they call ScaleRL. What makes this specific recipe so reliable and crucially resistant to those blowups we talked about?
Right. The recipe combines three key things: stability mechanisms and smart data curation. The first mechanism is implementing an asynchronous setup. Now, traditional async RL for these huge models often suffers from stale rollouts.
Meaning the policy is learning from data generated by a much older version of itself.
Correct. And if the model is learning from really outdated examples, those importance weights we mentioned can easily blow up.
Okay, so how does ScaleRL fix that staleness?
They adopted something called PipelineRL with K8. Basically, it's a system where the weight updates are pushed out to the policy generators much more frequently, within 8 steps in their case.
Ah, okay, much tighter loop.
Much tighter. It significantly reduces idle time and ensures the training distribution stays much closer to being on policy. And that improvement directly boosts the slope. By dollar makes training more efficient, and it also seems to nudge the asymptote slightly higher just because of the improved overall stability.
Okay, stability mechanism 1.
Yeah.
Better async. What's next? Let's talk loss functions and precision, often the source of numerical nightmares.
For sure. They identified that one loss function, CISPO, generally outperformed another common one, DPO, specifically on the asymptotic reward, mostly because CISPO just maintained a much steadier improvement curve, especially at very large scale. DPO seemed more prone to high variance.
Okay, so CISPO is more stable. What about precision?
This was a critical, almost surgical fix they found. They compute the head, just the final decision layer for both the policy generator and the value trainer in full FP32 precision. The rest of the model can be lower precision, like BF16.
Why restrict that costly FP32 precision to just the head? Why not the whole model?
Because that final calculation seems to be where numerical instability often peaks in these setups. By ensuring just that last layer for both the policy and the value functions uses full 32-bit precision, you avoid many of the subtle numerical mismatches that can cause those importance weights to suddenly explode.
Like making sure the very last digit of a big calculation isn't rounded off too soon, which could throw everything else off.
That's a good analogy, yeah.
Yeah.
It prevents those errors from propagating catastrophically.
And the result of just this small targeted fix, is it noticeable?
Oh yeah, highly quantifiable. They showed this head-only FP32 change specifically lifted the performance asymptote, addregores, from about 0.52 up to 0.61 on their standard benchmark.
Wow, just from that.
Just from that. It costs very little extra compute overall, but it demonstrably locks in a higher potential ceiling for the run.
Okay, that's a big win. The final component you mentioned was data curation, which they described as basically free wins in efficiency. How does that work?
Exactly. This is all about making sure your expensive GPU hours are spent maximizing learning, not just processing noise or churning through problems the model has already completely solved.
Makes sense.
They implemented two specific steps here. First, drop zero variance prompts. If a prompt generates the exact same response every single time it's tried, well, it contributes essentially zero useful gradient to the policy. It's just noise at that point.
Get rid of the useless stuff.
Right. Second, they instituted no positive resampling. Basically, you keep track of how well the policy performs on specific prompts over time. And you stop resampling any prompt that the policy consistently aces. They defined aces as having a pass rate at or above 90%.
So you stop feeding the model, like kindergarten level problems, when it's clearly ready for calculus homework.
Precisely. This frees up valuable compute cycles for the harder examples, the ones still on the frontier of the policy's capability. This improves stability and effectively lifts the ceiling, $8, by ensuring the policy stays focused on learning new things.
That makes a lot of sense.
And they also mention using prompt-level aggregation for rewards, which helps ensure that maybe one massive, high-reward task doesn't completely dominate the gradient signal over, say, 10 smaller but still important tasks. Keeps the learning more balanced across the board.
Okay, this gives us a really complete playbook. So if I'm planning my next big RL run, the source material actually divides my decisions into three really useful buckets. Let's frame this for the listener. What should I scale based on what I actually want to achieve?
Right, it provides clear guidance. Bucket 1 focuses on decisions that fundamentally shift the ceiling. If you absolutely need a new level of reasoning depth or just the maximum possible quality, you have to prioritize features that expand the policy's core representational power.
What does that mean in practice?
It means things like longer context lengths. They showed 32K token runs eventually surpass short context runs, even if they start slower. And crucially, it often means larger models. For instance, the study showed a 17 billion parameter mixture of experts model, and MOE could actually outperform an 8 billion parameter dense model while using far less total RL compute time.
Because the MOE just had a higher inherent capacity, a higher potential ceiling from the start.
Exactly. Its parameter A was higher.
Okay, bucket 2 is about speed. Decisions that improve efficiency. So if I have a fixed budget or a tight deadline, this is where I focus.
Correct. This is where you implement that ScaleRL infrastructure we discussed, the asynchronous setup like PipelineRL, the robust loss function like CISPO, and you definitely apply that surgical FP32 head fix. These are the steps that ensure you climb your S-curve as steeply and quickly as possible to reach whatever ceiling your model and data allow.
Makes sense.
Yeah.
Get there faster. And the final bucket is more like maintenance. Decisions that avoid wasted compute.
Yep. These are sort of the housekeeping items that increase the trustworthiness of your runs and reduce cost variance. We already covered dropping the zero variance and the already solved prompts. Another key one here is batch-level advantage normalization. This helps provide a steady, reliable learning signal to the policy, regardless of the specific rewards that happen to be in that particular batch.
So smoothing things out.
Smoothing things out, yeah. These changes don't necessarily raise the theoretical ceiling dramatically, but they make sure you don't stall out unexpectedly or waste, say, 10% of your expensive run on totally useless computation. It makes the whole process more reliable.
Okay, so bring it all together for us. What is the final recommended workflow for a team that wants to adopt this methodology? How do we actually use this sigmoid curve to predict the future of our run?
The recommended principled process boils down to this. You run your chosen ScaleRL recipe with all the stability fixes and data curation for about half of your total target compute budget.
Okay, half the budget up front.
Right. Use that accumulated data from the first half to fit the parameters of the sigmoid curve, find your A, B, and C mid. Then you extrapolate that fitted curve out to your full budget to predict the final outcome.
And then you decide.
And then you decide. If the prediction shows a strong finish, a high ceiling that meets your goals, you scale the run-up with confidence, commit the rest of the budget. But if the extrapolated ceiling looks disappointingly low, well, you cut your losses, you stop the run, revisit your architecture or hyperparameters before burning the remaining half of your budget on a run doomed to plateau too early.
It really transforms RL from that chaotic black box into more of a reliable engineering blueprint.
That's exactly the shift.
This feels like a truly revolutionary change. We started this conversation talking about RL scaling being this unstable, unpredictable gamble.
Yeah, alchemy.
Alchemy, right. But now we have a principled forecasting tool based on this sigmoid curve. We have a tested recipe for stability with ScaleRL, and critically, a way to decouple that short-term efficiency from the ultimate performance ceiling. RL scaling really does feel like it's graduating from, gut feel and vibes to a proper engineering discipline.
I think that's fair to say, and perhaps the greatest implication here is the democratization aspect. This framework potentially allows smaller teams, maybe open source labs, to test a new algorithmic idea at a more modest scale.
How so?
They can adopt this standard curve-fitting protocol, estimate the idea's scalability much more reliably, and then prune the dead ends, the ideas that hit a low ceiling, without having to burn these giant compute clusters every single time they want to prove out a hypothesis.
That could seriously speed up innovation across the entire field, not just inside the big labs.
Absolutely. It lowers the barrier to entry for experimenting with scalable RL.
Okay, so here is the challenge for you, the listener. Drawing directly from this incredible work we've been discussing, don't just, absorb this information passively. Try to apply the discipline. Choose one scaling knob this quarter. Maybe it's batch size, maybe context length, maybe model size. Run a half-budget experiment using the ScaleRL principles we talked about. Fit the sigmoid curve to your results. And then plan the rest of your run with actual numbers, not just vibes or crossed fingers.
Yeah, make a data-driven decision.
Exactly. Your next breakthrough in reinforcement learning AI should ideally come with a plan, not just a prayer.